good morning, and welcome. How many people have done anything with WebAssembly or looked into it at all? No, this is new. It's early days for the technology. I started talking about it earlier this year, and I was a bit concerned that it might still be a little bit too early, but there's been a lot of activity in the last 6 months since the browsers entered their preview mode in February. And so it's a very exciting time. Now the problem is there still isn't a lot of there aren't a lot of tutorials out there. There's not a lot that's easy for people to get exposed to in the first time. So my goal today is really just to get you excited about what's coming and to make you interested in looking further into it and to point you in the right direction. I'll make sure that the conference organizers get the slides because there's a lot of links to places for you to look and things to play around with. But mostly I just want you to kind of get a sense of what's coming and why this is going to be interesting. So we'll start with an introduction to the problem. We'll look at sort of a stepping stone towards getting there called Emscripten. We'll look at where sort of WebAssembly is now and kind of how the fundamentals work, and then take a look at what's coming next in terms of the future. This is a very demo-driven talk, so I'm hoping the network holds up. Apologize if it does not. So here's a question I'm almost afraid to get the answer to. How many people remember life before the web? Okay, I don't feel too old. That's enough of you raise your hands that you're with me on this one. I was exposed to Mosaic the week that it came out, and it just blew my mind. Right? I had been an Archie user, an FTP user, Gopher user, and a friend of mine showed me Mosaic, and I really understood the impact, but at the same time, I didn't necessarily connect in my head the hypermedia information spaces of the web to what I was doing in school and the work that I started getting into when I first graduated, which was C, X, and Motif, and then very quickly C++ and OpenGL. I worked on the world's first whole Earth visualization environment, so think Google Earth, but 23 years ago. And I've always been an advocate of the web. I spend a lot of time talking about REST and hypermedia and linked data and semantic web and stuff like that. But it wasn't until along the way that I started to think about web development and software development in the same sense, right? The web was about Ted Nelson and Tim Berners-Lee and Paul Ole and Vannevar Bush and people like that. And then the software development was more about Knuth and McCarthy and Kernighan and Ritchie and right, just the worlds just didn't collide in my head. And certainly the development experience was nothing alike, right? Initially it was just hand editing HTML files, then we got a little bit better about generating them. Along the way, Netscape was introduced, and there's this weird thing called JavaScript that emerged. And for a while, you were actually considered a more serious programmer if you didn't know JavaScript, right? Because it was just a toy. It was a toy for popping up menus. They stole the name Java to be cool. And it was something that I just didn't spend a lot of time looking at because I was off doing serious software development things. And then somewhere along the way, things changed, right? We started to see the performance improvements in the toy technology called JavaScript running in the browser. And again, I was even attuned to what was going on. I was attached to what became, I believe, one of the first, if not the first, books on Ajax, and then ultimately decided I didn't want to spend my time on that because it didn't seem like everything was ready yet to me. Obviously, I was wrong on that. And so as we started to see the performance improvements in the browser, people started doing more and more interesting things with them. And then that sort of translated into the development of Node and doing more interesting things with JavaScript on the server as well. And so suddenly the world of what's happening in the browser started to feel more like software development and less like just the hyperspace or hypermedia world of the web. And it was in this space then we started to see the emergence of new APIs, and HTML5 came out that standardized how audio and video were handled and whatnot. And we saw the emergence of WebRTC as an in-browser, non-plugin technology with JavaScript APIs for manipulating the connection to peers across the world, across networks, doing NAT translation as needed, with the peer channel discovery mechanism, the data channel mechanism, and it was all being done within the browser without barriers to what was happening in the browser. It's not a plugin, right? With Flash and Java applets and things like that, there are memory barriers, whereas here, we can start to apply CSS filters directly to the video that's coming in off the stream. And it was this marriage of the capabilities of HTML5 with the JavaScript APIs from WebRTC, with the evolution and support of CSS3 and things like that. And we can now combine CSS and Canvas and video all in one thing. So we're starting to see this emerge as a rich platform. At the same time, we see the emergence of WebGL as a way of having hardware-accelerated 3D graphics in the browser, also without the need for plugins and whatnot. So this game called CubeSlam is a WebGL-based game that uses WebRTC. If you wanted to play a friend, you could generate a link, send them the link, it'll do the network peer discovery and the network address translation, and you can end up playing them. And it uses the WebRTC data channel to send movements and updates in the game back and forth. Then this is obviously being done within a browser with hardware acceleration of the 3D graphics. So our platform is evolving into these incredible capabilities, and really exciting things are coming out of them. We see the emergence of WebTorrent as a torrent capability being built on the back of WebRTC. And if you haven't seen this, I absolutely encourage you to look at it. Within seconds, I will be streaming high-definition video from people all over the world, and then showing it here in the browser. And so we now have the ability to find and discover peers and share large amounts of information in real time, and this is all fantastic. The problem is, we have to wait for the browsers to add support for these low-level things. Things like the network discovery, the network jitter management, the bandwidth usage, handling the HD displays, and the video streams that are coming out of them, and doing some of these transformations. These are all low-level things that we would want to be able to be very performant and high performance. We're not going to do that kind of stuff in JavaScript, but the JavaScript APIs that the browsers end up supporting take advantage of capabilities that the browsers have built in at the low-level C, C++ library level. And so we're kind of at this point where we're happy with where the platform is, but the delay to get the browser vendors to agree upon things and then support those standards with polyfills and stuff like that along the way, that takes time, and it takes time to innovate. And so WebAssembly is emerging as a way of solving some of these problems, allowing us to do low-level coding stuff and yet still have it be accessible within our JavaScript environment. Now, Google started something like this called Pinochle, and they have basically since abandoned that because it did not have the right characteristics in terms of interoperability with the JavaScript, in terms of being cross-browser. And Mozilla had a project called ASM.js to show how we could have some of the same native kinds of performance and still maintain JavaScript interoperability. And that basically sort of fueled the thinking that eventually became what we have come to know as WebAssembly. But on its face, right, this definition of WebAssembly as being a new, portable, size and load time efficient format suitable for compilation to the web. That doesn't sound very exciting, right? That doesn't seem like some kind of next generation thing that you got up early to come to the first talk today to see. So let me take you through exactly what this is going to mean. Number one, this is not WebAssembly. This is using ASM.js in its initial form. But just to give you a first step in, I'm going to run a Qt application directly within my browser. So if you're familiar with the Qt cross-platform user interface toolkit, right, this is a Qt application, and it's running in the browser. That's kind of cool, right? I can take it a step further, and here's an animated tiles demo. So it's downloading JavaScript and the engines that are emulating the low-level code, but the performance is pretty amazing, given the fact that we're sort of emulating an environment that the Qt platform can run in. Now, as I said, that was not WebAssembly, that was ASM.js, so let's look at WebAssembly. And you'll have to forgive me here, I'm terrible at this game. But this is a Unity engine-based game that's now being run in the browser without a plugin. Everything that it needs to download and to run, it does so. It downloads what it needs through WebAssembly modules. So here we see I win when nobody else is playing. Okay, that's kind of cute. Well, how about this as another WebGL, WebAssembly interaction using Unity? Running in the browser, no plugin. I am equally as bad at this game. But just think about that for a second. Think about what is possible now that we're able to do these sorts of things within the browser without having plugins by using low-level languages like C, C++, and being able to run these applications in there. We see where we're going even further, assuming the network works here well, should do okay, using this one final platformer game. It is worth it, so give me a second just to let it download. Notice it's just downloading JavaScript and elements, and it's compiling it down into a format that it can be used. And now we have the capacity to do AAA kinds of games in the browser. The web becomes a platform for deploying desktop native kinds of applications. And doing so in a way that does not require us to have to care about distinctions between Linux and Windows and OS X or Mac OS, right? Because the libraries are compiled into an intermediate representation that is JITted. Sorry, I have to hit that a couple times to break out of the van. So I can jump up and slide down. Anyway, you get the idea. This is a AAA quality game that is now being available in the browser. But I don't have to worry about waiting for browsers to support particular low-level kinds of capabilities. I don't have to worry about downloading the right library, because the intermediate representation will be JITted into native format as needed by the underlying engine. Now, before we had the support in the browsers, we had Emscripten and ASM.js as a step in this direction. And Emscripten, as a technology, allows us to compile C and C++ into JavaScript by way of LLVM bitcode. So if you're not familiar, LLVM is a backend that a lot of languages have started emitting the intermediate representation for, and a lot of the optimizations that go into the backend research are applicable to the various languages then that emit the LLVM IR code. So we don't have to have parsers and optimizers for every single language. We have something that will do the parsing, emit the bitcode, and then we can take advantage of optimizations in a platform-specific way. So the idea is to take C and C++, which already were supported with LLVM parsers, and then convert the generated bitcode into JavaScript. And the idea here is that the semantics of translating bytecode into bytecode, or bitcode into sort of bytecode, is a lot easier and faster than trying to map one language to another. And the semantics of one language and what's possible in one language into JavaScript. And then the idea is once you have sort of like C and C++ based scripting engines, like Python, like Lua, then those languages can run on top of this JavaScript backend too, once they have been ported into this platform. Now, why are we doing this? Is because the JavaScript engines are getting faster and faster and faster, and this is where a lot of the momentum is in terms of optimization. The JVM has a lot of, many years of optimization in it, but I would say more effort is now being put into making V8 and the various other engines faster. We also have a lot of people who still have a lot of familiarity and experience and whatnot with non-JavaScript languages and the tooling and the build systems and everything that goes into that, so we want to be able to capture that. And JavaScript still kind of sucks, right? I mean, there's a lot of good things in it, but in terms of, as it's maturing, we have all these sort of like weird states and plugins and transpilers and some support for the new module system, and it's still kind of a mess. And people would like to be able to use different kinds of languages on the web. So the idea is, if we can compile these other languages, C and C++ are the starting points, but there are already Rust converters to generate this in the back end. People are looking at doing similar sorts of things with Go. Right now, WebAssembly does not support garbage collection, but in future versions it could, and that would open it up to other types of languages that could be generated and supported on the platform. I'm not going to follow this link, but there are hundreds and hundreds of other kinds of some language to JavaScript tools out there, but they're all sort of like hand optimizing, hand converting, hand mapping, and it's amazing that they work as well as they do. This is just an attempt to get some more consistent, coherent momentum behind bringing other languages to the web as sort of first-class citizens. Excuse me. So Emscripten as a tool chain was designed to make it easy to do these kinds of conversions and to be able to bring these native languages to the platform that runs on anything from PCs to Linux to Mac OS X to iPads and iPhones and things like that. And so C++ developers don't have to learn JavaScript. Tools and tool chains and things like that don't necessarily have to be overly modified. And we don't have to take these pre-existing libraries and make them available for different platforms when they can just be compiled down. So as a very simple example, right, we have main. It calls the standard I/O function printf and then returns. There's nothing weird about this. There's no weird annotations, no weird pragmas or anything. We can just take the Emscripten compiler, compile it. It will generate some truly god-awful JavaScript. Don't look at this late at night. You'll have nightmares. But what comes out can be run as a Node application. It can be run in a browser. And I'm sorry, you can't read this, but it says hello world. It's within the browser environment. It's executing the same framework and producing the same results. And it's not just for toys, right? We have support for things like libsdl and OpenGL and other kinds of libraries that are available to be used within this platform as well. So Emscripten was a step along the way, and they added support for generating WebAssembly backend directly, not just the asm.js output. And so we'll see an example of that in just a minute. But WebAssembly itself was designed to be a stack machine. It's designed to have a size and load time efficient binary format. The binary format makes it easier to parse. It makes it easier to send across the network because it takes up less space. And then the idea is with the just-in-time compilers and the native interpretation being already well handled on the individual platforms for V8 and whatnot, we will achieve near native execution when the code is running. And so it's a little bit like the difference between sort of hand-optimized C++ versus JITted Java. It can take a look at how the system's actually running and make optimization choices based on that. Now, if you've been paying attention in the news at all in the last couple of years, the idea of running native code in the browsers should scare the crap out of you, right? But it doesn't actually have that kind of potential because we're moving away from having direct pointer support. We have chunks of memory, pages of memory that are then interpreted as pointer references and whatnot, but we don't have the same pointer kinds of capabilities expressible in the intermediate results. And so it's actually, it'll need to go through further security investigation, but it is already a fairly secure environment. Now, the idea is that this can run within browsers, and when it does, it'll enforce same origin policies for the WebAssembly modules like anything else, but we also have the ability to run it outside of the web browsers as sort of a native standalone application that can be used in embedded system kinds of scenarios as well. What we want is we want to be able to have good development tools. So there's an intermediate format, a textual format based on S expressions of the ASTs. So we'll see some examples of that in just a minute. The idea here is we want that to be easy to read. These textual formats that will assist in debugging and being able to help developers understand what's going on as this code is passed around. But also allow them to do further optimizations based on these structures as well. But one of the things that cannot be underscored enough is that this is also an attempting to be part of the web. And the web has certain characteristics, and we do not want to throw those characteristics away just to achieve some kind of optimized form. The web supports versionless interactions. It supports, this idea of backwards compatibility and evolvability such that people don't have to be locked into this version of this library running on this version of the OS in this version of the browser. Right? We want things to be more flexible and change friendly. And so WebAssembly was designed to be part of that. So the main concept is that we have these modules of code expressed in ways that can be exposed functionality. Currently, you can only interact from these languages with JavaScript itself, or the other way, you can call from JavaScript back into these native methods. But in subsequent versions, as I said, there's a goal to have garbage collection, there's a goal to have the ability for these other languages to manipulate the DOM directly. And so there's some really exciting things that are coming. They tried to not be overly ambitious and then produce nothing. So the MVP, the minimum viable product, has some fairly serious limitations, but it's also an attempt to give people enough of a platform to play around with such that they know what some of the optimizations and hurdles that they may face as they move into what they're now called the browser sort of preview mode, right? Where all the browsers are supporting it in some version, and they want to see what people do with it. They want to see what problems they come up with, and then they're reforming a new W3C working group to extend the standards in new directions based on what they find. All right, so the binary format, if you just look at gzipping source code, right, that works pretty well. And so there are some people who advocated the very simple approach for doing that. And if you just take the ASM.js code and gzip it, you could get some pretty good size reductions. But we also, in putting it in this binary format, also got the same size reductions and then had the ability to be able to look up indexed binary names rather than parsing strings in the structures. Huge performance improvements came from that. But by taking this approach, this layered approach, they have the opportunity for taking further advantage of advancements in structural optimizations over time. So the first step in layer 0 is just to have a simple binary representation of the modules so that it's easy to parse, easy to send across the network, and already we have some reductions there. The layer 1 will allow local optimizations to take advantage of structural relationships in the code, finding dead code trees and things like that down the road. And then at the end of the day, they can put a high-level compression layer on top of it just to compress whatever is there. If they just compressed it in the first place, then they would lose the capacity to do a lot of these other sort of optimizations. And so that's the thinking behind that part of it. The textual format, as I said, is a series of S expressions. So the most simple S expression that's valid is just an empty module with no functions. This would get translated into the WASM equivalent of the magic numbers in the version numbers, but nothing else is really going on here, so there's not a whole lot to do there. In general, the structure of the module is going to have a series of function definitions with signatures that have some local variables, and then a series of instructions in the body. So We will see a simple example of this in just a moment. The arguments that are being passed in can be parameters of, at this point, only ints and floats, 32-bit and 64-bit ints and floats, and they can only return a single value. So a lot of these, again, are going to be modified in subsequent versions. They just didn't want to have to get into supporting funky esoteric structures and whatnot in the minimal viable product. So because they come in this order, you can ask for the local values through positions, or you can give the parameters and local variables names and then refer to them through their names. Now again, keep in mind, this is not how you're necessarily going to be programming. There's nothing stopping you from programming at this level, but you're going to instead probably be writing C, C++, Rust, something like that, and this is what gets emitted, and then this is what gets converted into the binary format, and then optimized and JITted locally when it's running within the browser. This is sort of the intermediate textual representation. So here we see a fully functional version of a module. We give it a name called add. It takes 2 parameters, and then it has a single result. As a stack machine, the operations are intended to manipulate the stack in meaningful ways. So the first get local will pull the value from the LHS param and then push it to the stack. The second local will get the RHS param, push it to the stack, and then the I32 add instruction will pop off 2 integers from the stack and then push the response to the stack, and then the value that remains on the stack is what will come back through the return value. So this is generally how this is going to work, and then we export the add function from the module. So it's now going to be visible to anybody who parses the structure of the module. Now, the JavaScript to do that is going to look something like this. So this fetch and instantiate is a helper function that comes with a library called wasmutils.js, but you can see that it looks just like the same kind of normal promise-based stuff that people are familiar with. So we could say fetch and instantiate the module called add in its compiled binary format. We haven't talked about that yet, but this is what it's going to expect. And then that is going to fetch the bits, generate a buffer, instantiate an instance of the module in the browser through the WebAssembly JavaScript API, which is part of the definition of the minimal viable project, and then it's going to create an instance that the JavaScript environment can interact with. And notice then once it has the instance, it just says, call through the exports collection the method called add, pass in the functions 1 and 2, or the values 1 and 2, and then this will generate 3, because obviously it will add those 2 numbers together. So we can see that calling stuff into the native functions will work relatively straightforwardly, right? It'll look just like other JavaScript function invocations. But oddly, I can define function calls within the modules that I want to use and leave them as externally defined, and then satisfy them with local JavaScript functions. So when I instantiate the instance of the module, I can hand it a JavaScript object that says, satisfy the log function with console.log. And then stuff can be logged from the native language through JavaScript tools. So even though we cannot yet manipulate the DOM directly, we have some certain limitations. Once we can call into JavaScript, within JavaScript, we can do whatever we want to do there. So it's a surprisingly powerful combination given everything that is available to us. Now, you're going to have command line tools to do some of these sorts of things, but just to give you a sense of how this works, I'm going to use a tool called WASM Explorer. I'm going to pick an example. So in this case, we'll look at a factorial function. And so we'll see here, actually, it will not allow me to zoom in, but basically this is just double fact takes an int, does a factorial calculation. Notice over here we see that this has been compiled into the WAST S-expression textual format. We can see that the assembly is available here. We see that it can be run. but we can also download the WASM locally. So if once you're playing around with these, if you have some libraries and you don't necessarily want to set up all the tooling and everything, there's nothing stopping you just doing all this directly from within the browser. So here's the C code, you want to compile it, generate the WASM from it, download it, and now you can instantiate it like you just saw me do on the previous slide. But obviously, right, you have the ability to do other sorts of things. So queue sorts and whatnot. So the idea is we can take advantage of things like the hardware-accelerated 3D graphics in WebGL, and we can connect them up to existing numerical libraries written in C or C++, and they can all run within the browser without having to worry about native versions of libraries and nonsense like that. And that should start to give you a sense of what's going to be possible with this combination. Another quick example, WASM Fiddle is another tool that's available to you. So you can play around here. You could say, I realize it's very small, but I can add in like a new function, foo, that takes an int. We'll call it x, and we'll return x times 3. I can say build that. We can see it generate the text format here and run it. Obviously, I'm not doing anything with the foo function, but we see that down in the corner, the console says 42, which is what the main is returning right now. So we have the ability to play around, to see how C code gets translated into this. But with Emscripten, you're also able to generate those. And again, I'll show you an example in just a second. I'm not going to go here, but if you want to see sort of what the limitations of the MVP platform are, webassembly.org/docs/MVP is the best place to go. It'll talk about not just the decisions that were made, but the motivations for the decisions as well, where we are, and what the next steps are going to be for the platform. There's also a series of use cases, so they're going through and talking about building things like document and video, or image and video editing tools within the browser, being able to do sort of AAA game platforms. So we don't need a Steam, we don't need a console, to handle these sorts of things. You can write these games and deploy them to various platforms, and they will have near native performance, but all the benefits of running within the browser as well. So you get a sense of what other people are expecting to see from the emergence of this platform as well. If you want to play around with Emscripten and WebAssembly, it's as simple as cloning this GitHub repo, running these tools to install and activate it, and then there's a shell script or a batch file to source these to set up the environment. There's a lot of trickery in terms of where it finds the LLVM version that it's using and the other tooling, so you want to be careful about that. But basically this sets you up so that you can then take your hello world, or whatever it is you're trying to do, use the emcc, pass in the C files, pass in the compiler directive to emit WASM on the back end. You can give it the name of a HTML file to generate to have sort of the bootstrap infrastructure for running within the browser, or you can obviously generate code to run within Node as well, using outputting the WASM tools. And then there's a sort of a standalone web server, particularly if you're using Chrome or something that doesn't like pulling stuff off of the file system. So to avoid same origin policy problems, emrun will run out of a browser, and then the Emscripten scaffolding framework will work just like it did for the ASM.js stuff I showed you earlier. Except now we're using the WebAssembly backend, not just the JavaScript. So there's a lot more that you can do with this. We obviously don't have time to go into it all. But I do want you to sort of have a couple of takeaways and some more things to get you excited about this. Number one, as I said, it's early days. And not everything is going to make sense, particularly once you get into the various conversions and marshalling things into and out of the formats. There are some things that are just not going to make sense to do natively. And so as you start to play around with these things, right, you can look at, here is a JavaScript implementation of the Fibonacci calculation, and here's the WebAssembly C code. And we see that that's not substantively more or less code one way or the other. The code is not all that much more complicated. And when we run it, we'll see, given the gains that have happened in the optimization of the JavaScript platforms in the last couple of years, the gains aren't always dramatic. This is a pretty good one, but some of the other examples here, you'll see parity or even the JavaScript running slightly faster. So just like in the early days of C and C++, hand-optimized C and C++ could run circles around Java, but as the Java VM optimizations got better over time and we're able to look at actual runtime sorts of things, there were cases where it would make more sense or you could get comparable performance out of it. So we're in early days in terms of the optimizations that are available, but as you saw with the games that were being played, they're still quite good. And so the decision when to shell out to native code and when not to is going to have to be a measured one. It's going to have to be based on whether you have already written code in these languages that you want to bring into the browser, whether you're going to start from scratch and use a different language or just do it in JavaScript. We don't have hard and fast rules for those things yet. And the answers will change as the optimizations get better over time. But we're starting to see more and more capabilities come in. So this is doing some edge detection, in this case using WebAssembly against video coming in off of WebRTC, and we can sort of see the frame rates and the time. And if I switch to JavaScript, inverts it just to show you that you're running in a different mode. I don't think it's trying to say that JavaScript is the dark side or something. But we can see that there are comparable performances depending on whether you're using the C++ SOBA libraries or the JavaScript ones. But we're starting to see more and more like real uses show up almost on a daily basis. So it's a very exciting time to start to pay attention to what's going on here. But we're also seeing real stuff start to happen. So this is an actual deep neural network implementation. Everything is done entirely in the browser here. They go through and they talk about the process and how they get there, and they've got a WebAssembly engine, but they also have some Web GPU backends. Web GPU is an API that Apple is starting to support. But so looking here, the whole concept of neural-based style transfer allows you to take one image and take another image and then basically interpolate from the one to the style of the other. So I can say, take this picture of this dolphin and sort of apply the color schemes and the style of the wave, the very famous Japanese painting, to that image. And it doesn't have to be just a simple image. We can get back to our friend WebRTC video camera and do the same thing. I look like Neptune or something, I don't know. But again, the thing to keep in mind is this is all being done within the browser. And so given that the browser, as its value proposition, has to do with being a universal zero installation platform, the fact that we can now write things in native libraries, native languages, things other than JavaScript, and get near native performance, and the benefit of zero installation, and get the sort of promised write once, run anywhere of the JVM, and you start to see why these are all going to combine to a very, very sexy combination of capabilities. All right, so where do we go from here? The site wasm.news is a good site. It's updated periodically to look for the emergence of new projects, new tools, new approaches. Back in March, right, they announced that the Lua VM is now running in a WASM environment. So once the engine runs in the WASM environment, then Lua should run successfully on top of it. We're starting to see loaders for Webpack and people, looking at other sorts of tooling and whatnot. So wasm.news is a good place to find to track developments there. The the first couple images with the JIT curves that I showed you comes from a great little cartoon introduction by Lynn Clark. It's called the Cartoon Introduction to WebAssembly. But she's a very strong advocate for what's happening in this space and is writing a lot about it. So she's talking about now that the browsers are all in this preview mode, what are the next things? So being able to invoke function calls between JavaScript and WebAssembly in a faster way. She explains what the problems are and how they're going to improve. Improving load times, and then looking at things like letting WebAssembly directly modify the DOM. And so code that you're writing in one native language can now modify the HTML environment that it's running in on a completely different platform. Doing some shared memory concurrency things, doing some single instruction, multiple data kinds of parallelism, so to take advantage of multiple CPUs and GPUs within this environment. A better story on exception handling, which basically means a story on exception handling. Trying to make it so that the errors that happen within these native modules are easy to consistently trap and deal with in JavaScript. Moving into things like garbage collection, building better tooling that supports these sorts of things. So this is where we're going, but it'll take a while until we get there. So we'll see lots of open source projects starting to emit the WASM binary, doing conversions between the text format, parsing new languages that are not requiring garbage collection. A lot of cool things like that will happen in the interim. Now, where I want you to think about this is to think about the fact that all of this is now happening within the browser. So this video has nothing to do with WebAssembly, but this is just him showing what it means to now be able to do WebGL in the same rendering context as the DOM being rendered and the DOM being manipulated. So now we have three-dimensional objects that are able to coexist with actual DOM elements that are still interactable, right? And so as you'll see in just a minute, where he goes, taking these ideas a step further. So now that we can mix together hardware-accelerated 3D graphics, low-level peer discovery, network address translation busting, the ability to send arbitrary data to these peers over these data channels, the ability to build WebTorrent-like capabilities on top of these APIs, and then now being able to link in modules and capabilities expressed in native low-level languages that are able to achieve native performance in this environment without having to wait for the browsers to support new JavaScript-based APIs to expose those to the JavaScript environment. You'll get a sense of how the web that you know is going to be very little like the web that's very quickly going to become our daily experience. And the whole concept of desktop applications can start to disappear. The things that we like about direct manipulation can be embedded within scenes. So now we have a Minecraft engine with a television component, where the television component has buttons that you can click on, and yet the rendering environment is still DOM-based, right? And so the YouTube video editor can be there. You can change channels to watch different YouTube channels, and you get a sense of where all this is going, right? Combining near-native optimization of these languages with the environments that the browsers have evolved into is going to be very, very, very exciting. The fact that it's being done in this incremental way, in a safe way, is very powerful as well. But I hope that you are interested in digging a little bit deeper. So here's my email address. I'm happy to take. We have a couple minutes for questions if there are any, but I will get the slides available to the conference organizers. But if you have any questions, please feel free to contact me as well. So thank you very much, and I'll be happy to take any questions if there are any. Yeah, so for similar reasons, right? Back when UI development in the browser sucked, the people who were the serious software developers were the Java developers, and so we kind of thought to ourselves, well, we'll fix that problem in the browser because we know what we're doing. That worked out well, right? Now we're heading in the other direction. Like the people who are doing all this innovation within the browser are saying, man, that back end is kind of slow and kind of sucks. We'll fix it by pushing our shared libraries and stuff to the back end. But we're now moving to this environment where the platform can run in a browser or not in a browser, and can run code written in arbitrary languages on arbitrary platforms, targeting other kinds of arbitrary platforms. And so there are similarities to things that we've seen before, but I think we're going to start to see these in embedded devices, in cars, in Internet of Things tools and things like that. And we're going to see, I think, this become a very successful, if not the successful, VM platform moving forward. So that's a common question. The idea is, like, if this really takes off, are people going to just stop using JavaScript? And I think the answer is no, right? There's an entire generation of people who grew up using this, and this is the language that they're most comfortable with. This is the language that they think in. The point is, we don't want the entire future of the web tied to a particular language. And so as new languages emerge, people can make the choice to do some innovation and emit something that will run in high performance on the platform and interact with the languages that people are comfortable with. Or if you have legacy code that you want to bring into the environment, it will do it as well. I don't think this in and of itself is going to displace JavaScript, right? I think other languages and the capabilities and the experience of using them will have an impact on whether people use JavaScript or not. This is just a way of letting it all basically work together. And nobody's, Brendan Eich is a big fan of WebAssembly, and he thinks that this is going to change everything. So this is not let's hate on JavaScript, it's let's make it interoperable with all these other languages as well. Any other questions? Right, so currently the question is, what about multi-threaded applications? Currently, the MVP does not have good support for that, but that doesn't mean you can't do threading in JavaScript and then reach out into the languages. There are ways of sharing module instances within JavaScript environments, but some of the very next step sorts of things that they want to be able to do is to have shared memory concurrency and other forms of parallelism to improve what's possible. For right now, it's not as strong as we would want it to be, but in the near future it will be. All right, well, thank you very much, and please enjoy the rest of your day.